Hi, this is the third video in this little video series about the special orthogonal group and the orthogonal group, the second one in each case, SO2 and O2. And in the last video, we introduced a general form of a rotation matrix. We are talking right now about SO2, and you see we will continue to be talking about SO2 up until here, because SO2 is the one that has the rotations. You remember we talked in the first video about taking the plane, and what SO2 does is it rotates the plane with about a fixed point here. And then if we look at the larger group O2, well, that has the rotations in it too. It has SO2 as a subgroup, but it also has reflections. For instance, I could reflect it across this horizontal line, keeping that point in the same place, or across this vertical line, or across some other line if I wanted to, keeping that point in the same place. So I've been calling these groups, and in particular I've said that SO2 is a subgroup of O2, but we need to see that they really are groups. In other words, that they satisfy the group axioms. So we want to ask this question here. Why is SO2 a group? And that's the same here, except here I've been more explicit about what SO2 is. More explicit but less formal, maybe, saying, calling it rotation matrices. So I'm just rephrasing this question here. Why is SO2 a group? So this is the question. Now, an answer, which is sort of an informal answer, is because if you perform two rotations in a row, I guess I'll say consecutively, that's more mathematical, right? So if you perform two rotations consecutively, you get another rotation. Before I spell it out, you should think, what group axiom does that correspond to? So that's one thing, that's one reason. Composition of rotations is associative. Now you could say, okay, well now I'm going formal on you. I said this without using any mathematical words, and here I'm saying associative. I could try to give some tortured explanation of putting together three rotations, putting together the first two and then the second one, or putting together the first and then the second two together, but that would be a waste of time. Composition of rotations is associative. So that's the second group property. And then if you do nothing, it's a rotation by 0 radians. So what group property is that talking about? And then finally, and if you rotate backwards, you can undo a rotation. So in all these words, this is this is an informal answer for why SO2 is a group. In all these words are built in the group properties, the group axioms. So I'll put another A here, and this is a more formal answer. So, of course, the way that we perform two rotations will be to multiply together two rotation matrices, and I'll show you this in a second. But so multiplication of rotation matrices yields another rotation matrix. I could say this more formally. I could say that the family of rotation matrices is closed under matrix multiplication. You may have seen it in that expressed in that way. Multiplication of rotation matrices yields another rotation matrix. So that's, well, I'll pair these up in a second. Matrix multiplication is associative. That's the second thing. Now, the identity matrix now this is just the matrix 1, 0, 0, 1 like this, is the group identity and the matrix. There's a number of different ways I could write this. Because I said here rotating backwards, I'm just going to change the sign of the angle. So I'm going to write the angle, and then you can work out with what these are using symmetry properties, but I'm just going to put minus theta, minus sine, minus theta, and then sine minus theta, and cosine minus theta. This matrix is inverse of, should be the inverse of, but I'm running out of room here, so I'm cheating. So cosine theta minus sine theta, sine theta, cosine theta. Okay, now I've really filled up the board here, and these are two. This is a mouthful, and this is a mouthful. So I'm going to have to prove for you all of these properties, justify for you these properties. But let's first of all pair these off, pair the informal statements with the formal statements here. So this first statement I'm saying here, so this will be 1. If you perform, let me leave out the because there. Let's start my 1 here. If you perform 2 rotations consecutively, you get another rotation. That's the same thing as saying, so this will be 1 here, multiplication of rotation matrices yields another rotation matrix. So that 1 pairs with this 1 here. Those are equivalent. So let's start at 2. So this is second statement here. Composition of rotations is associative. And here, what corresponds to that is that matrix multiplication is associative. And that's true for any matrices. They don't have to be rotation matrices like these are. And then number 3, if you do nothing, it's a rotation by 0 radians. Well, this identity matrix here, so this is, or number, this are 3 here. This identity matrix here is precisely the, and I drew over it, sorry. The identity matrix here is precisely the matrix that does nothing. It doesn't rotate, it leaves the vectors alone. And then number 4 would be, if you rotate backwards, you can undo a rotation. So this would be number 4 here. Rotating backwards means taking this angle minus theta, so that's going in the other direction rather than theta. So these are 2 answers for why SO2 is a group. but I've just stated them. I haven't proven for you that this is true. So let's wipe this off and then we'll go into a little bit more detail. So we had our informal answer, we had our formal answer, and then the sort of final answer that we want is we're going to say that we're just going to check the group properties. So we're actually showing that our formal answer is true, or at least we're going to check part of it. I'm not going to show associativity of matrix multiplication. That's a nuisance, and it's something that you can assume on more general principles. So the first thing to check is that matrix, let me put it this way. Let's say, I'll use this closed idea. I mean, you have to know what it means anyway, and it's a short way of saying it. So let's say that, let's see what it means for this to be closed under multiplication. So what would this mean? And this is a little bit of a nuisance to show this. So what this would mean is that if I have a matrix, let's start out with, well, I guess before I write angles in here, I'll do a little example. So this is sort of an aside, and this is an example. So if you rotate by pi over 4 radians, and you do it twice, you get a rotation by pi over 2 radians, and I'll show you this happen. So if you like degrees, once again, this is 45 degrees, that's 90 degrees. And so the idea is that, I'm going to write this up here and then erase it because I need the room down there, is that if you start out, you know, say I start out with a vector that goes here and I rotate it by 45 degrees, and then I rotate it by another 45 degrees, so this is going up pi over 4 and another pi over 4. Well, those two add up to give you a total rotation of pi over 2. But let's see that really happen with the matrices. See, the way you would do this is you would start with any old vector you want, and so you would have A, B, and then you would rotate, and you remember the matrix that we used to do this. It was this one. Right? That was rotation by pi over 4 radians. Now, whatever I get out of this is going to be another column vector. So this is another vector. And it should be rotated by pi over 4. But then I want to rotate that by pi over 4 again. And so what I have to do is multiply this whole thing by that same matrix again, because I want to rotate it by another pi over 4. So what we ought to get, now I'm going to erase this little part down here. What we ought to get, what we had better get, if this is going to work, is we had better get that the product of these two matrices is rotation by pi over 2. And what would that say in terms of what the entries of that matrix would be? Well, you can use that formula and figure it out. Cosine pi over 2 is 0. And we ought to get then a minus 1 here, because sine pi over 2 is 1. 1 here and 0. So we ought to get a particularly simple form for this matrix. Now, we don't care what the vector is here. It should rotate it for any vector. What we really need to check is that this is really true, that it comes out to this particularly simple form. And let's see if it does. So let me take off the AB here, because that could be any vector, we don't care which one. And let's multiply this out and see that you really do get this here. Well, take the first row here and the first column here. We get square root of 2 over 2 times square root of 2 over 2, and then we get minus that same thing. So we get a 0 here. This top row, the second column, we get a square root of 2 over 2 times a minus square root of 2 over 2. That gives us a minus 1/2. And then this gives us another minus 1/2, so we get a minus 1. And you can see the rest of the entries are going to do what you want. This one is going to give you a 1/2 plus 1/2 is 1. And this one, these are going to give you a minus 1/2 plus 1/2 is 0. And so that checks out. Now this doesn't prove closed under multiplication yet, because we just showed it for a particular little example. But I wanted to illustrate this happening before we write out the way it looks in the general case. So let me scrub off most of this. So what we want in the general case is here we ought to have, you draw a little rotation over here. Say we rotate here first by theta, and then we rotate by another additional angle, and I'll call that phi, Greek phi. Well, then what that's telling you is the total rotation should be by an angle theta plus phi. Now, what would this say in terms of matrix multiplication? Well, it would say first I'm rotating by, now I'm going to draw a vector here, but then I'm going to take it off, because once again, it's not going to matter which vector it is. The idea is you start with a vector here, and you want to rotate that by theta. How do you do that? Well, you use that matrix. Cosine theta minus sine theta, sine theta, cosine theta. And now I get some vector. This is just some other vector. And now I want to rotate that vector. See, we started out with this, vector, and it could be any other. I mean, I could start out with one that starts somewhere else and rotates by that same amount. But just for simplicity, I'm showing the one starting out here. I want to take that resulting vector and I want to rotate it by phi. So I give us cosine phi minus sine phi, sine phi, cosine phi. And when we do that, then we will get these two, well, this is three matrices multiplied together, really, right? A 2 by 2, 2 by 2, a 2 by 2, and a 2 by 1. Now, we know by associativity that it doesn't matter what order we multiply them in. So in particular, we can multiply this whole AB thing by this part here. And this is the part that we care about, because we could use any vector here. We want to see we get the correct rotation matrix there. And what would that correct rotation matrix be? Well, it had better be, if that geometric thing is correct, it had better be the matrix cosine theta plus phi minus sine theta plus phi, sine theta plus phi, cosine theta plus phi. That's what it has to be. But is that what it really comes out to be? Well, let's check it. And to do so, I'm going to scrub off some of this. I'm going to take off my little commentary here. I'm going to get rid of the vector because we don't care what vector it is. We can multiply it by the matrix later once we've assembled this matrix, because it's associative. It doesn't matter whether we multiply it by the vector first. So we're going to multiply this matrix out and see if we get this. Okay, well, this first entry here is going to give us, watch what it gives us. It gives us a cosine phi, cosine theta, That's this and this minus sine phi sine theta. And you know, I think I'm going to trade positions of these things. This will take 30 seconds. Hopefully you have an additional 30 seconds to spend watching this video. Here's what we're trying to check. We're trying to check that this thing really does equal cosine. I was going to run out of room, so that's why I'm switching positions. This will be theta plus phi minus sine theta plus phi sine theta plus phi cosine theta plus phi. And so this is what we want to check. So let's write out what this actually gives us. And that's what I started to do there, and then I erased it because I knew I wasn't going to have enough room. So let's see. So we get cosine phi, cosine theta from that one, minus sine phi, sine theta. And then for this one here, we get minus cosine phi, sine theta, minus sine phi, cosine theta. That's the first two. And then here, now this minus doesn't follow after this. See, this matrix is divided into 4 entries, of course. It's a 2 by 2 matrix, so you can imagine little lines dividing it there. And then this one gives us a sine phi cosine theta plus cosine phi sine theta. And then the final one gives us a minus sine phi sine theta. And then plus cosine phi cosine theta. Now, if you haven't been in trig, or if you haven't been in trig for a long time, this looks awful. You're like, how would I simplify that? It turns out that each one of these, now this is separated the same way here, as far as the entries go. Each one of these is a trig identity, okay? The fact that this equals this, that's actually one of the trig identities that they made you memorize in trig back in high school. I don't know if you remember, but this one here is a trig identity. I mean, you're used to seeing it without the minus sign, and you're used to seeing the angles in the other order, but it is an identity nonetheless. It's the one you're used to for angle addition. If you look up, if you put like angle addition identities or something onto Google, or just look in a trig book or calculus book or something, all these things are here. And then this 3 here, this is a trig identity, and this is also a trig identity. Now, what I'm not going to do is prove these trig identities. I just want you to recognize that these are identities, and these are things that you're allowed to assume. So let's scrub all this off. You can rewind and watch as many times as you like. Let's scrub all this off and put a check mark by this closed under multiplication thing that we had to check. See, that's the first group property. Now the second one was associativity. And we were already assuming this in the little computations we did there. And it's true for any matrices. So this is always true for any matrix multiplication. And so I'm not going to check it. You know, you could work it out for 2 by 2 matrices or something, and maybe it's something everybody should do once in their lifetime and then never again. And I've already done it once, so I'm not going to do it again. That's always true. It's like, in any case, it's something that doesn't have specifically to do with these groups. It's something that all matrices satisfy this property. Now, the third thing was the identity. We had to check that there was a group identity. And I told you what it was. It should be this 1, 0, 0, 1. And so how would you check this? Well, you just have to check that this rotates any vector by 0 radians, that it does nothing to it, and you know this, so A, B, what happens, this is any old vector. The first row in the first column picks out the A. The second row well, there's only one column. The second row picks out the B, and this is the same, so that checks. And then inverse is, well, I wrote out what it was before. I guess I'm running out of ink, but I'll write it out one more time. Here I just wrote minus theta, and then so there's a minus sign minus theta, and then a, now this is the inverse of that one there. It's not the inverse of the one with the phi. It has to be the same angle there. And then this is sine minus theta. That's messy. And then this is cosine minus theta. And, well, what I'm going to ask you to do is look back at this part 1. See, I had written on the board, and I've showed you that those trig identities, I pointed out to you those trig identities, when I multiplied these out, you got the addition of the angles in there. Well, what will happen is if you take the second angle, which is phi, to be minus theta, then this will all be obviously true, because what you'll end up getting is just cosine 0. I keep wanting to write a theta there, because what this will be, this will be theta plus minus theta, because that would be the phi there. So this will be cosine, get this to stay here. So it'll be cosine, I did it again. So it'll be cosine 0 minus sine 0, sine 0, cosine 0. And you know what those are. That's 1, 0, 0, 1. And that's the identity, which does nothing. So what that tells you is that if I performed this rotation, if I applied this rotation matrix, and then I applied this one, the combination of those two would be the identity matrix, which does nothing. And that means that this is the inverse of that, because it inverts whatever that one did. It undoes it. So I think I've shown you enough here. Maybe there's a few little gaps left here and there in terms of proving this, but I think you can understand pretty thoroughly now why the rotation matrices form a group. And next video we'll see a geometric way of understanding this group structure. So let me check that off, and we'll talk about identifying the special orthogonal group SO2 with the unit circle in the next video.